Okay, in this flip lesson, we're going to look at mechanical waves. More importantly, we're going to look at some of the phenomena, some of the behaviour we see of mechanical waves. Mechanical waves in themselves is a fairly simple concept. It's more some of the behaviours and phenomena we observe that is more interesting. It really just give you a summary of those in this flip lesson. We will look at a number of these in the lab in a more hands-on way. I'll also direct you towards some simulations that will help you explore some of these things. But this is really just supposed to be a bit of an overview and an introduction to some of these that we will then explore more further. Let's get into it. So, a mechanical wave is just a wave that requires a medium to travel through. So it travels through something by making the particles that make it up vibrate. So whether that is a sound wave that makes the air particles vibrate as it travels through, whether that is like a seismic wave, which is basically like what earthquakes produced, and they're also used in mineral exploration, which are basically sound waves that travel at very high speed through the ground and make those particles vibrate, or they're both examples of longitudinal mechanical waves. We can also have transverse mechanical waves if we think about the waves in the water on the ocean. So the first phenomena that we will briefly talk about is an echo, and I think probably everyone knows what an echo is already. Generally, we refer to them when we're talking about sound waves, but all sorts of waves can be reflected. If you remember in that last flip lesson, you saw the waves being reflected off the end of the slinky spring and coming back to me. But basically, a reflected sound wave is an echo. It's not much more to that. It's probably something you already knew. Didn't need to come here to learn that. The next phenomena that we'll talk about, which relates to the echoes in a sense, is reverberation. A reverberation is a reflected sound wave that follows so quickly that it cannot be distinguished from the original sound. One merely receives the impression the original sound has been prolonged. So generally, for two sounds to be seen as distinct, they need to be at least 1/10 of a second apart. If they're less than 1/10 of a second apart, our ears will tend to hear that just as one prolonged sound. The way we'd demonstrate that, if we had the right space, is we'd sort of go and find a wall that was fairly isolated and there was nothing near it, and you can bang two blocks of woods together, and initially, if you're very close to the wall, you'll just hear that sharp sound. As you move away from the wall, you will hear that sound get longer and longer. And generally, if you get more than about 17 metres away from that wall, and I'll talk about why 17 metres is important in a minute, past that, you will hear the sound that's reflected as a separate sound. So you'll hear two distinct sounds. It'll be an echo. The speed of sound in air is about 340 metres per second. So that means in 1/10 of a second, sound will travel about 34 metres. So if we're talking about an echo, if you make a noise, it travels 17 metres, it bounces off the wall, it travels 17 metres back to you, then it's travelled 34 metres, that's taken about 1/10 of a second. Reverberation is really important in terms of acoustics when you're trying to design buildings and picture theatres and music halls and all those sort of things, because you don't want too much reflected sound waves bouncing around. They create a noisy environment and they make it difficult to distinguish and hear sounds and listen to things. So that's why you'll often see in things like picture theatres, is probably the one you might be most familiar with, all the heavy curtains at the side, because they're made of materials that are designed to absorb sound waves, so they're not reflected and causing reverberation. If you play guitar, or guitar's the one I know about, there's probably other musical instruments, I'm not very musical, you will also know that you have a reverb button, and that reverb button on a guitar, in a sense, what it does is it turns them from being sort of quite sharp, crisp notes into more longer, twangy notes. So as you turn up the reverb, you get more of that longer, twangy sound. So that's reverberation. The next one is resonance, and again, I'll direct you to I'll probably direct you to a video that you can watch to demonstrate resonance on a really large scale in a bridge. In the classroom or in the lab, we'll also look at some smaller examples of resonance in using springs and also maybe using a guitar. You can actually use the principle of resonance to tune a guitar, and that's something I can show you potentially in our visits, or if I remember my guitar. But if I don't, it's not the end of the world. So what is resonance? Every object has a natural frequency at which it vibrates. So if you've ever played a xylophone, you'll know that all of the blocks on the xylophone give a slightly different note because they all like to vibrate at a different frequency. If you've played a guitar, you'll know each string vibrates and gives a note at a different frequency, depending on the thickness and tension and all that sort of thing. Now, something special happens if an object is forced to vibrate at this frequency, and that is we can get a very large amplitude vibration established. So if we just make an object vibrate at any random sort of frequency, we won't necessarily get really large amplitude vibrations. But if we can force something to vibrate at its natural frequency, we'll get a really large amplitude vibration. Now, if that's a bridge, that can cause the bridge to basically shake itself to pieces and deconstruct. If that is, I'm not sure if you ever get those annoying rattles in your car, something in your glove box, or even sometimes the mirror on the car. Basically, that's because the movement of the car, there is a vibration that corresponds to the natural frequency of the vibration of that object, so it sets up that really large vibration. I know there's a couple of songs in my car that if I play will make my rear vision mirror shake quite vigorously because the frequency that is in the song, they're usually really low bass type frequencies, corresponds obviously to the frequency that that mirror wants to vibrate at it, and so you'll get a real shaking of that mirror when you play that music that corresponds to that frequency. With a guitar, the way I'd show that is basically, I'm not sure if anyone's played guitar, I'm not very good at guitar, but I know enough that if you hold down the 5th fret on the top string, it'll play the same note as the 2nd string. So what we do is we hold down, if a guitar's in tune, hold down the 5th fret, hold the top string on the 5th fret, and we put a little bit of paper and fold it over the 2nd string. We don't touch the 2nd string, but then we pluck the top string. Because that creates a vibration that's the same frequency as the 2nd string, you'll see that paper generally just start to vibrate really vigorously and jump off that string. Not because you're touching the string, but just because the nearby vibration of the same frequency of the top string sets up that large amplitude vibration, which is what resonance is. So yeah, that's echoes, reverberation, and resonance. The next one actually before I go on there's also some other interesting things around standing waves and beats. If we get a chance, we might look at some of those, but they're less common and they're less important to the sort of things that we're going to do. But the next one I want to talk about is the interference of waves. Now, this one happens with both mechanical waves like light, but it also happens with electromagnetic waves. So we'll talk about it now, but just remember the interference of waves can happen with either mechanical waves or electromagnetic waves that we'll talk about in the next flip lesson. The interference of waves says, well, the basis of that is the principle of superposition that states when two or more waves travel in a medium, the resulting wave at any moment is the sum of displacements associated with the individual waves. What does that mean? It's probably easier to picture it with these diagrams here. If these two waves are travelling through the same space, basically we will get superposition, so the combining of these two waves, and we will end up with something that basically has twice the amplitude when we add these together. So we call this one here constructive interference. This occurs when two waves meet that are in phase. And by in phase, we mean the troughs line up with the troughs, the peaks line up with the peaks, the troughs and the troughs. When this happens, we get this larger amplitude wave and we get constructive interference. When we get the opposite of that is destructive interference. So if we get two waves that are out of phase, that is, trough lines up with peak, peak lines up with trough, and when we add those together, they cancel each other out and we don't see anything. We call that destructive interference. Now, this happens with water waves. We will demonstrate that, or you can go and explore now, and I'll put this link up as well. This simulation that lets you explore wave interference, both in terms of actually light and sound waves, or water waves. I do have a ripple tank in the lab that we used to use, but to be honest, the ripple tank takes forever to set up, and it doesn't show it anywhere nearly as clearly as the online simulations, so we'll probably just stick with the online simulations. So yeah, we will explore, we also explore a lot more constructive and destructive interference, particularly with light, in Year 12 physics if you go on to Year 12 physics. So that is the interference. As I said, that can happen with both mechanical waves and light waves. Okay, I didn't probably keep that as short as I wanted to, but hopefully that gives you a good introduction into those terms, and we will explore those more in the lab or with the online simulations. Cheers.